Oh, sorry, we've had so many technical difficulties. Oh, okay, great. It was turned out to be our auxiliary webcam, so we're going to improvise here and use this screen. I am so sorry about that. Hey Nicole. We are joined here today by Dr. Steve Lee, who has been waiting patiently right beside me, and we'll go ahead and we'll skip our first few introductions and reminders and whatnot, and we'll jump right into Dr. Lee's presentation just for the sake of time. And then at the end of this presentation, if we have time, we'll run through our activity, which is Recipe for a Planet. Greg, if you are there and can insert Recipe for a Planet into the chat box. Let's see if I can get a better... Yep. All right. So not quite what we planned, Steve, but if you will go ahead and pull your slides over.
This is called Murphy in action.
I know. We can launch a lander to Mars, but we can't launch a webinar. So we'll just move this computer screen right over here. So just to give you guys a little bit of a background on Steve, he works for the Denver Museum of Nature and Science as a space scientist within their children and adult programming. He also works here at Space Science Institute as a research scientist, and he works primarily with Mars. Is that correct?
That's right.
Okay. So once again, I apologize for the not great camera angle, but will that work, Steve?
I think it will.
Okay, great.
How do we get to the first slide?
Yeah.
Since that's the last slide. Well, good afternoon. I guess it's afternoon for everyone. And I think I met quite a few of you at the my library conference at the end of February. So some of you will have seen some of these slides before. So you can go and get a cup of coffee for a while if you'd like. But what I wanted to talk about today is sort of an overview of just what we've done exploring Mars over the years, and then how the InSight mission fits into that, and then some details about the mission itself. So if we were doing this 100 years ago, we'd probably be talking about the Mars you see on the left there, which was a much more fanciful view than our current understanding of Mars based on lots of years of having spacecraft there. And then on the right is the Hubble view of Mars taken about 10 years ago. And that's Mars as a planet, which is the way that we understand it today. But, if we were to move back several thousand years ago, we basically knew Mars as a bright reddish star moving in the sky. And in the early days, so to speak, every ancient culture, Mars represented the god of war. And it was that way for multiple thousands of years. And it really wasn't until the 1600s then that we started having technology that we could point at the planet. And the early version of that was telescopes. And in 1659, the very first documented observation of Mars through a telescope happened, and that was made by this Dutch astronomer, Christian Huygens. And the sketch on the right is his rendition of what he was seeing through the telescope. And so that gets us up to more recent past, late 1800s, early 1900s. Lots of people were observing Mars through telescopes. And this fellow, Percival Lowell, did a lot to popularize Mars. He spent much of his life observing the planet. These are some of the photographs he took. So we got beyond the point of just doing pencil sketches. We actually had cameras that we could attach, and this shows that Mars was a highly variable place. And in the early days, it was assumed that all of the dark stuff was lakes oceans, seas, things like that. And Lowell carried that one step further, saying that all of that stuff was actually where there was enough water to support vegetation on the surface. And he drew maps like this, which had the classic dark markings, but they're all interconnected with this spider web of lines. And his belief was that there was an intelligent race of Martians on the surface, and that they had built this global canal network which carried meltwater from the polar ice caps in the spring down toward the equator, and they used that to irrigate their crops and fields and forests. And that accounted for all of the variations that we saw. And so that sort of belief held sway up until the 1950s, when we finally started getting instruments on telescopes that could determine what the temperature of Mars was. It was actually fairly cold. Determined that the atmosphere was fairly thin. Determined that the atmosphere was really not at all like the Earth's atmosphere. It was mostly carbon dioxide and not a very nice place to imagine. And so in the 1960, I'm not sure why we're okay. In 1960, we finally sent our very first spacecraft to Mars, or attempted to. And this is just a schematic of all the different spacecraft that we've sent. Actually, this only goes up until 2012 as far as the graphics go, but there's actually been 51 separate missions that we've sent to Mars starting in 1960. The first successful one of those was in 1964, and that's continued on up through the current day. But over history, less than half of those missions have actually succeeded. So we've got something like a 45% success rate or whatever. So Mars is really hard, but we've also had a lot of success. So I would argue that other than the Earth's moon, we know Mars better than any other place in the solar system. In fact, we probably know it better than the Earth's moon.
Right.
Just because we've had so many different global observatories there.
So it looks like China and Russia and Japan have also sent missions.
China has not.
Okay.
Japan has. The Europeans have. Mm-hmm. Russia certainly has, or the Soviet Union back in the early days. And in fact, right now, I think there's 6 spacecraft orbiting Mars.
Oh, wow.
The Indian Space Agency has one. There's 2 from Europe, 3 from the United States, and then 2 American rovers on the surface, which we'll talk about a little bit later. So it's it's a busy place right now, and it's about to get busier because we're going to be sending a couple of other spacecraft in 2020. There's a whole fleet of spacecraft intended to go to Mars. So just sort of a quick overview of the types of things we've seen over the years with these spacecraft. So from orbit, we can see that the wind is actually very active on the surface. And this is like an abstract Van Gogh drawing or something. It's very puzzling at first, but what we now understand is this is a sand dune. It's got frost on it. That's the sort of bluish, whitish stuff. But the dark curlicues are where dust devils swept the surface clean of the bright reddish dust. And you see the dark material that's underneath the dust. And so that's active today. If we came back a week from now, this pattern would look very different in all likelihood. And we know from these years of observations that there are dust storms that that happen all over the planet. This is a regional dust storm on Mars up near the North Polar Cap. And it's not by any means a small phenomenon. The scale bar in the lower left, that's 150 kilometers, or roughly 100 miles across, and that storm is 3 times that. So it would cover the entire state of Colorado if it was happening here. And then there's the big daddy of dust storms, and those happen every several years, and that's a global dust event. And this is an example in 2001. On the left is a view of a particular hemisphere of Mars. On the right is about a week later, showing the same location on Mars, but the entire atmosphere globally is choked with dust. And that lasted for several months.
Wow.
And so that, we now know, is what causes all of these brightness changes that we see. Periodically, you just rain a sort of a bright layer of dust down onto the surface, and at least temporarily, all these dark features are covered up with bright dust. Mm-hmm. And then subsequently, later in the year, the wind becomes effective enough again that the dark areas get swept free of dust and become dark. So that's what all the changes are about. So that's one major thing. And then the other thing we've determined is that at some point in the past, Mars had a lot of water running around. This is a dry riverbed. We see these all over the planet as well. But what's puzzling about this, or important about this, I guess, is currently the atmosphere is so thin and so cold that you cannot have liquid water on the surface. It's just physically unstable. It either freezes or evaporates. And this says that at some point in the past, the Martian environment was very different. It would have had to have been much thicker atmosphere, much warmer atmosphere, and a lot more water available. And so that's one of the things we're trying to figure out is what was early Mars like? Was it mild like this, if you want to call it mild, long enough that life could have formed on Mars? And a lot of our spacecraft have been orbiters, and so we're very familiar with the surface of Mars, the surface geology, and it has some really amazing features. This is Olympus Mons, which is the largest single mountain in the solar system. It's about 80,000 feet tall. It's about
2.5 Everests.
Right, and it's 350, 400 miles in diameter. So lots of topography there. There's also a huge canyon system that it actually extends about a quarter of the circumference of the planet. So if this was on Earth, it would stretch from, say, Boston to Mexico City. It would just be a rift across all of North America. And so, Mars is a very interesting place. There's obviously has been a lot of geology going on. And so we've been, over the years, I showed that one graphic where we've started in the 1960s to send spacecraft. Starting around the early 2000s, we've had a much more focused plan, and that plan really involves figuring out the role of water on Mars. It's called Follow the Water, sort of a mantra. And it's involved both orbiters and landers. And so I wanted to spend a couple minutes. This is a mission that I have been working on for about the last 15 years. It's called Mars Reconnaissance Orbiter, and it was launched in 2005, got to Mars the next year, and has been returning data almost continuously ever since late 2006. And I was involved in building a couple of the cameras on board. And so the one camera is sort of a weather satellite camera, if you will. It gives you, or allows you to construct color global images of Mars, similar to what we'd get from a meteorology satellite. And that allows us to track these changes that we know happen over a long period of time. And just to prove that I was there, this was back when we were testing the camera. It was built by a company in San Diego called Malin Space Science Systems, and a number of us went out there to calibrate and test the camera. This is a closer up view of the camera. It's only, I mean, the back end of it is like the size of a deck of playing cards.
Oh, wow.
It's got a couple of fisheye lenses
Okay.
that give you 180-degree field of view, and so you just sort of act like a scanner. The spacecraft is orbiting from pole to pole. It looks under the spacecraft, and it returns a swath of whatever's directly underneath the spacecraft. And then every 90 minutes, it comes back around. The planet has rotated a bit, and so it gives you a different locations on the planet, and you can assemble all those strips together to make a global view of the planet. And so this is an example of one of those. And if you look in the upper right, these are two global maps or semi-global maps that were taken a few months apart. And you see, I'm not sure if you have like an arrow that we can
Oh,
move,
yeah, certainly.
So right here.
Right here?
No, right, that dark thing right there. So that's what I want you to look at. And that's about 500 kilometers or so across. So again, the size of a western state like Colorado. And we come back, that first one was in August of 2009. This is in December of 2009. And you see that feature has gone away. And this is a closer up view of it. So this is one of these classic dark features that have been observed through telescopes for, since the 1800s. And suddenly it's gone. And we would have expected that it would have recovered by now, and the bright dust would have blown away, and it hasn't. It's still, 9 years later, it still looks like it does right there. And so that anytime you see something that is behaving very differently, that sort of gives you a focus, because you think you understand the planet, and then something like this is an exception, and that can tell you a lot about what the processes are. If they're not quite so repeatable or not quite so understandable, and so we're spending a lot of time just monitoring this. Hopefully, at some point, while the spacecraft is still active, it will go back to its former appearance, and then we'll be able to figure out why it took so long. So anyway, that's what I spend my time on. But I'd mentioned that there's a variety of different spacecraft, and that we have this sort of long-term path for exploring Mars. So I'm sure most of you remember the Spirit and Opportunity rovers that landed in 2004, and one of them, Opportunity, is still roving on the surface. But those were designed to be robot geologists. They were really looking for evidence that there had been liquid water in the two landing sites, and they found it. So that tells us that, yes, there was available water running across the surface at some point. And then in 2012, the next generation of rovers, the Curiosity mission, landed. And that's more of a geochemist. It actually can determine the composition of all the rocks that it's looking at. It can determine what the environment was like when the rocks were formed. And so with that, we're looking for evidence of, could the environment have supported primitive life if there was water there? And we've also found definitive evidence that yes, there was running water in this location.
To answer Nicole's question down here, she said, did the rovers find liquid water or evidence of liquid water?
So they found evidence that liquid water had been there, and it's partly the chemistry of the rocks.
Like hydrated
minerals. There's one mineral in particular called specular hematite, which is, you've probably seen it, it's sort of this gunmetal looking beads often that you can buy jewelry made out of. That stuff, it's an iron sulfate, so iron and sulfur mixed together, but that's really good evidence that those minerals were dissolved in water. You had groundwater coming up through existing rocks, and the hematite then precipitates out of the water. The rocks get wet, and you alter the composition of the rocks by whatever's dissolved in the water. And we also see at the Curiosity site, they've driven across effectively a dry wash, like an arroyo that you'd see in Death Valley, where the little pebbles are all rounded, and that says that they were tumbled in flowing water, and it wasn't just a single flood, it was a long period of water flowing, or at least repeatable flows of water to provide that sort of structure to the rocks. So, and what we don't know, and we're still trying to figure out, is how long ago was the water there, and how long did it last? And that's a really active area.
And what caused that disappearance of water?
That's right. I mean, we're investigating that. There's a mission in orbit right now called MAVEN that's investigating how the atmosphere went away, because apparently in the early days the atmosphere would have had to be much, much thicker than it is currently. And we think it all has to do with the fact that the Martian interior, or the Martian core, solidified at some point, or at least the magnetic field turned off, and that protects the planet from the solar wind. So over the last couple of billion years, the solar wind has been slowly stripping the upper atmosphere away.
Wow.
And we've got really good evidence for that now, because that's what MAVEN has been studying.
So we should be thankful for our magnetic field then.
Yes,
okay.
Absolutely. It's what saves us. So, okay. So then in 2008, we had an Arctic explorer, and it was designed to go up near the Arctic Circle of Mars and see if they could find permafrost, where you've got ice under the surface. And this, let's see, about right there is where it landed, a little bit further south than that. And when they dug into the surface, they had a little backhoe, and indeed, just about 10 centimeters down, they ran into a layer of ice. And that's exactly what they were looking to find. And all the white stuff in that image is frozen water. And so that says there's probably a lot of water under the surface. So if and when we send people there, that's a resource. You can melt it, you can drink it, you can use it to grow things, and you can also break it down into hydrogen and oxygen, which gives you rocket fuel for your flight back home. So that was an important discovery. And the one reason I show this is the design of this spacecraft. It's basically identical to what the InSight mission is.
It looks familiar, yeah.
And so that saved a lot of resources on this new mission. You've already sort of got the experience knowing how to build one of these things, and you just put different instruments on it. Okay, so now let's finally get to where we need to be, which is talking about the InSight mission. And every mission needs a good acronym. And so instead of saying today we're going to talk about the interior exploration using seismic investigations, geodesy, and heat transport mission, we just say let's look at InSight. And so what this is really intended to do is look at the interior of Mars for the very first time. And the reason that we look at the interior is that tells us a lot about the evolution of the planet, and the interior is where much of the energy comes from that drives the geology. And so if you have a liquid core, then that heat has to escape. That drives volcanism, as it does on the Earth. You might have things like plate tectonics, which we have on the Earth. So we know a lot about the Earth. We know a lot about the Earth's moon. We really know very little about the interior of Mars. So what this mission is going to do is be similar, or get us up to the point where we were about 100 years ago on the Earth, where we had seismometers, where we could look at the signals from earthquakes, and those waves travel through the interior of the Earth, and depending on the structure that's in the interior, you get different results. And so that's what we're going to be doing with InSight. And what we want to do then is fit that into our understanding of the whole formation of planets in the solar system. And so the InSight mission has sort of three avenues of exploring the interior. The first is it's got a very precise seismometer on board, so if there are Mars quakes, we can do the analysis to figure out what the interior is like. It's got a mechanism for very precisely tracking the rotation of the planet, and that tells you a lot about the interior as well, depending on if there's a lump in the middle, the core, the planet will spin slightly differently. Mm-hmm. If the core is liquid, you'll see a little bit of sloshing, if you will, so there'll be some irregularities to the spin. And then also the flow of heat from the interior tells you a lot about that structure. If the core is liquid, you'll have a lot more heat coming out than if it's completely solidified at some point in the past. And so what we're starting with is that we think we sort of understand how planets formed, at least the rocky planets. And so early on, there's this cloud of debris orbiting our young sun, and a lot of that starts colliding and sticking. And the collisions can happen at a very high velocity, and so you get a lot of heat generated in this accretion process. And there's also a lot of radioactive material early on, and so that heats up the material. And as it forms, then eventually more or less the entire planet is molten in the early days. And that's what we call number 3 here of stuff happens. And those are the details that we don't quite know. But all of the research says when the planet was molten like this, then all the heavy stuff sinks to the middle. And so that's how you get a nickel iron core on the Earth. That's the heaviest stuff that's in this big ball of molten rock, and over a long period of time it sinks, and then ultimately you have lighter stuff floats to the top, and so that's how you get this multiple layers, where you have the core, which is the densest part, and then a mantle, which may or may not be still sort of molten as it is on the Earth, and then the crust, which is sort of the scum that floats to the top, and that's what we, of course, exist on is the crust. And so this number 3, where the stuff happens, that's what InSight is going to be addressing, is how did that happen? And so, we've got a lot of experience with the Earth now from the seismic data, over 100 years of research, and we think we understand the interior pretty well. And it's not simple. There's a solid inner core, there's a liquid outer core, there's this plastic sort of taffy-like mantle, and then there's an upper mantle, which is where all the lava comes from for active volcanoes, and then you've got the crust floating on the top. And the moon, we've had the Apollo missions actually planted seismic stations, and so we understand the interior of the moon pretty well as well. But those are the only two that we really have seismic evidence for. For Mars, it's mostly mathematical models of how the planet would have formed, and some of these models don't agree with each other, and so it's really important to try and figure out the details. Is the core liquid? Is it solid? Does it have a solid center and then a liquid outer core like the Earth does?
I see a lot of question marks by these measurements.
Right, and that's the point. We're trying to remove those question marks. And so we tried this the first time back in 1976, the first successful landed missions on Mars, the Viking missions. They carried seismometers, but the design of them was very crude. The seismometers were actually on top of the spacecraft itself, so they weren't coupled directly to the crust or the surface. And in fact, one of them failed completely. It didn't even turn on. And the other, all it succeeded in measuring was the mechanisms in the spacecraft itself. Every time the arm moved, you get a big seismic signature. You get a gust of wind, it would sort of thump the lander, and you get a seismic signature. They really got no signature for the surface or the planet itself whatsoever. And I'm not sure why this keeps... All right.
You want to go forward?
Frozen, yes. There we go. And so the InSight mission then will be the first time we've actually had a really good seismometer and hopefully a working seismometer on the surface. And that's the focus of this whole mission. And so there's sort of three parts to the mission. The SEIS is the seismometer. That requires a robot arm, puts the seismometer out directly on the surface. There's the RISE experiment, which is this precision tracking of the spacecraft. And then the HP cubed experiment, which is the heat flow measurement. And that's also fairly unique. It's got a little sort of a pile driver where it will drive itself about 15 feet down from the surface and leave little temperature sensors along the way. And so it'll be able to determine how much heat is coming out.
There's a cool video of them testing that out on the NASA InSight mission page. So Greg, I'm not sure if you're still in the chat box, but if you could insert the video link for the InSight Mars missions. If not, I'll post that afterwards.
Okay, so this is, if we can bring up the animation, this is how these experiments will be deployed. It actually will take about 2 months after landing to deploy the experiments, and they have to spend a lot of time with the cameras on board to trying to make sure that they're not putting it down on a rock or something that's going to interfere.
So everybody, Greg's posted a link in the chat box to where you can access these videos. I'm going to go ahead and play this, but if for some reason you have trouble with your bandwidth or if it's lagging, you can access the videos at the link that Greg posted below. So we'll go ahead and play this.
So this is the seismometer itself, which you notice that there's this cable that's trailed behind it, and that's where all the signals come through, and so they have to be very careful that that doesn't get tangled on anything. And then once the seismometer is on the surface, then they have this cover that they cover it up with, and that it's a thermal cover, so it provides insulation. It also protects the seismometer from the wind, and it's a sort of streamlined shape, and so if there is a gust of wind, it sort of flows over it rather than pumping it, and so that should minimize the signature of the wind. And then the second part of this would be the heat flow experiment, which it behaves similarly. It takes it off of the top deck of the lander and drags the cable behind it, puts it out on the surface. This one, the principal investigator, or the lead scientist on this mission, said this is probably the riskiest experiment on board, because this sort of little pile driver has to work. And if there's a rock 5 centimeters under the surface, it's game over, because it won't be able to pound through the rock.
Mm-hmm.
It needs to be probably 5 feet or more down before it would actually provide good signals.
So, Steve, that sequence we just watched, it was a minute and a half. How long do you think that's actually going to take?
It's the actual, once they decide where to put things, it's multiple days for each of these. It's a very slow, deliberate process. But on the schedule for the mission, they're expecting it to be a minimum of about 2 months from when they land to when those instruments are actually deployed.
Wow.
So they're going to be very slow and deliberate. Okay. So just very quickly, what is a seismometer? And one way to think of it is you just got a little weight on a spring. And if that's in contact with the surface, and if the surface vibrates a little bit, then the spring is going to bounce up and down, and the mass will bounce up and down. And the seismometer on board InSight is extremely sensitive. It can actually detect motions that are down like the scale of a hydrogen atom, which is incredible. And the one thing that was sort of a wow moment for me was hearing a talk about this. This is a test of the seismometer at the Lockheed Martin facility here in Denver, where the spacecraft was being assembled. And you see this sort of purple band through the middle of the plot there. And that's actually waves breaking on the coast of California. And we're able to get the seismic signature of those waves all the way here in Denver. So the better part of 1,000 miles away. And so I'm not going to go into this, but it's a complicated instrument. It's got many different pieces. It's by far the hardest piece to actually assemble and get it going. And so this is just sort of an overview of all those different pieces. And so then the question is, what causes any signals that it's going to get? And there's a variety of sources for seismic activity. One is if you've got stresses in the surface, sort of a la the San Andreas Fault, where something moves and ruptures. And that would be a fault letting go. So we'll be able to see that. Mars has 2 small moons, and so there's tides as the moons orbit overhead, so we'll be able to see that. We certainly expect to see meteorites impacting the surface, and we know from all these orbiting spacecraft that this happens multiple times a year, where something smacks the surface of the planet. So we should see that. And then there's the atmosphere. So you get storms going overhead, you get waves in the atmosphere, and that should cause a little bit of signal. And so it's a very complicated thing to sort that out. And this is just an example of if there is something that thumps the surface, then the way that the seismic waves travel through the interior of the planet is a very complicated thing. But that's what we're looking for, is to get these signals and then figure out what that structure is. So this is assuming that there's a mantle and a core, and you'll notice every place where one of these boundaries between the layers happen, then the waves change dramatically. They sort of get funneled around the surface layers. Some of them come directly through the interior, and well, it's that's going to be the payoff if we can actually figure out what that is. So at the top is the impact, or the Mars quake. At the bottom would be where our spacecraft is sitting, and by taking those measurements over the course of two Earth years, which is what the mission is expected to last, and as long as we have even just a handful of events that we can measure, that should provide enough data that they'll be able to tease out what the structure looks like. Okay, so this is just another schematic of that. The triangle at the top is our spacecraft. The little star at about 5 o'clock is the Mars quake, and there's various types of waves that travel through the interior.
I gotcha. Sorry.
So some of them go directly through, like this R1, it travels through the crust. R2 would be the wave that travels around in the other direction, and so those take a different amount of time to be received, and so that gives you a way to tell them apart. And I think the final one is that one, which would just be going round and round through the crust, and would take, it sort of circumnavigates the globe. Okay, and then the heat flow experiment, we already talked about it. They call it the mole, that hopefully will be able to pound itself down into the surface. And it sort of acts like a pile driver. It's got a little, once they put the pointy end of this down, it's got this little weight that a motor lifts it up, and then it drops it, and it provides a little bit of a thump. So over the course of many weeks, I think it, assuming it doesn't run into a rock, it's going to be able to pound itself into the surface. And then they'll have a couple of years of taking measurements. And then this is that RISE experiment, and what that is doing is trying to look at the location and the motion of the lander. And so they think they'll be able to pin that down to something like 10 centimeters,
wow.
6 inches in location on the surface. And this sort of the loop here is really what they're looking for, which is if the planet is doing that, then that gives you another angle of what does the interior of the planet look like. It will be different if it's got a big solid core as opposed to a liquid core, as opposed to no core. So to be able to figure that out. And so this then, I just wanted to end with this. This is a view of the spacecraft itself being tested, and so you can see the size of it. These solar panels are actually all folded up at launch, and so they're like Japanese fans. Once it's on the surface, they unfold, and of course that's what powers the spacecraft. And so we already talked about this. It's a very close copy of the Phoenix lander, so we already know about that. And the first on this mission it's not launching from Florida. It's actually launching from California. And that'll be the first time that a mission to another planet has launched from California. And so the launch window opens on May 5th, and it's about a month-long window until June 8th. So it'll take, regardless of when it launches, it'll arrive at Mars on November 26th, which is the Monday after Thanksgiving. And it'll take about 2 months to get those instruments deployed, and then it'll take about 2 years of data, and they expect it to last at least until November of 2020. The way these things usually operate is if it's still alive, so to speak, then they'll extend the mission, because the longer you collect your signals, so you beat down the noise in the signals and get a better product out of it. So, and this is just showing the trajectory of getting from the Earth to Mars. And so I think I want to end there. This is all about to happen. It'll certainly be lots of media around this from NASA, and so we hope that this will give all of you some tools to excite your library audiences and have them come back to you to get updates on what's happening with the mission.
Absolutely. So I think, guys, we lost a few minutes in the beginning with technical difficulties. So if you want to, before everybody has to leave and get back to the reference desk or do a program, if you wanted to ask Steve any specific questions, I think the last two questions are whether the Martian tides would affect the magma, or would it affect the dunes of dust?
I don't believe it would affect the dust at all. And the tides, compared to the tides on Earth, are very, very small. The Martian moons are tiny. They're captured asteroids in all likelihood, so they're only a couple of tens of kilometers across, and so they really don't have a huge effect. It's just that that's another source of a signal for our seismometer. That would be a weaker signal that would tell you other things, because it's very repeatable. I think Phobos, the largest moon, comes overhead every 7 hours or so. So it's just a good test. So it's not like on the Earth where we raise tides of a couple tens of centimeters in the solid crust of the Earth, and of course the ocean tides are even larger than that. So.
Okay. So what's the delay in from data reaching Curiosity to...
That all depends on the time of year. I think if the two planets are as close as they get in their orbits, it's about 15 minutes for the radio signals to go one way. If Mars is on the other side of the sun from the Earth, it can be about 45 minutes.
Oh, wow. Wow.
So the way all of these things work is typically you communicate with the spacecraft maybe once a day. You send commands up for what it's going to do for an entire day, first thing in the morning on Mars, and then it goes off and does whatever it's supposed to do. And then at the end of the day, it will communicate with one of the spacecraft orbiting overhead and send its data back from that day, and the scientists analyze it overnight and then give it its marching orders the next morning again.
Wow. So will it travel to Mars in the same, I guess Nicole means the same path, or the same travel means?
Very similar. It's sort of an ellipse centered on the sun, and so once it leaves the Earth, the orbit is designed so that it will cross the distance of Mars, or the Mars orbit, when the planet is nearby. And so one way to think of it is the spacecraft is flying by and the planet runs into it. and then they do their whole, it's called entry, descent, and landing, where
actually let's...
is its heat shield.
We have an animation of that.
That's right.
So we'll play this just for a little bit at least.
So this would be arriving at Mars. Typically they call this the 7 minutes of terror, because it takes about 7 minutes from when the spacecraft hits the upper atmosphere until it is sitting on the surface. And so it has a heat shield, slows it down to a couple times the speed of sound, pops a supersonic parachute, and then it will drop the heat shield. And when it's a couple kilometers above the surface, the lander separates, and it's got retro rockets, it fires, slows itself down, and stabilizes itself, and the pads, it will touch down on the surface. And then I think the next step is just showing how the solar panels unfold.
So a part of having that technology is that we're basing that on previous missions, right? We've already done that hard work. We've already designed the lander.
Right. We've designed the parachute, so we know that worked in 2008, which makes it a lot simpler and a lot less expensive than if you're starting with an entirely new design.
Absolutely. So maybe take one or two more questions for Steve. I do want to share some different resources with you guys that I didn't get to in the beginning. So we'll do, one or two more questions, and I know some of you all have to run back to your programs and your story time. Are they worried about the cords tangling? How would they fix that if it happens?
Okay, yes, they're very worried about the cords tangling, but I asked that same question of the lead scientist, and the cables are actually really stiff. There's, I think, 5 layers of material on those, and so it's sort of like, I don't even know what to compare it to. It's a little bit plastic, okay, but it's really stiff.
So a good bit of rigidity to
right.
It. Yeah.
And it really is designed to go sort of straight out, not twist to the side. And so that's their one protection. But they said if it gets hung up on something, almost certainly that's going to be the end of the show as far as that instrument goes, because they don't have a whole lot of, the arm itself is good at picking things up and moving them. It's not good at pulling hard.
Okay.
So that's one reason why they take so long to do it. They're very slow and deliberate. Unless anything has actually contacted the surface or gotten hung up, then they can move it back up. But it's definitely something they're going to be paying very close attention to.
High risk maneuvers. So Steve, I'm going to take a moment and I'm just going to go over a few resources. And feel free to chime in wherever you'd like. We have all this delicious sweets out to do an activity, but I'm not sure if we'll have time to get to it. So there's our agenda for today. Just wanted to point out, of course, if you guys aren't a member of StarNet, Greg asked if a rover could come help, so maybe they can call Curiosity over there.
The answer to that is no. They're too far away.
So, of course, StarNet's our online community of STEM professional development for librarians. So that's going to be where you can go to access these recorded webinars, blogs, forums, how-to videos for different resources, and so on and so forth. So just a reminder that Earth Day is coming up, so if you're looking for a specific program, a STEM program, to do some library programming around, this one is in 3 weeks, and of course you can do Earth Day programming before that, or after that. You can always do Earth Day programming. And we just did a webinar last month, so that last link celebrates 60 years of Earth observations with NASA. That's going to be a recording of that webinar. And then if you're looking for specific activities for Earth Day, I'd encourage you to check out the Earth Science collection on our clearinghouse, and the Earth Day collection, that's going to be our weather and citizen science activities. So there's a lot of great citizen science opportunities that you can do for Earth Day, including the Globe Observer app. And yeah, just go ahead and check out that webinar to hear all those awesome ideas. So we just launched registration for a May 17th webinar. This is going to be on the Parker Solar Probe launch. This is a really cool mission. and that it is going to, quote-unquote, touch the sun. It's going to come within about 4 million miles of the sun's surface. It will be quite hot. So come hear more about some heliophysics from actually our colleague, Dr. Paul Dusenberry. Many of our NASA at My Library partners know of Dr. Dusenberry. And again, for those NASA at My Library partners, there is a webinar next week as well, but that is only available for you guys. Steve's pretty much covered all of these, so I'm going to skip through that. And let's see, it's 2:07. I understand that some of you guys might have to go and leave. Steve, do you have a moment, or do you need a? So we might, we'll try to do a little small facilitation of this activity. We highlighted this. This is called Recipe for a Planet, and it is a food-based activity. I don't know whether that makes you excited or scared, but it is a way to kind of create a model of Mars and a model of Earth. I think today, because we're running low on time, maybe we'll just do the model of Mars, and we'll take a look at what that looks like. And I anticipate, as we find out more from the InSight mission about what the interior of Mars is like, we might have to adjust this activity over the next, 5 years or so. So we won't do the Earth model. We'll just do the Mars one, and then Steve and I will eat all the Earth ingredients after this.
Okay. But I'm definitely interested.
Yeah. So to make Mars, this is an activity. Again, you use sweets. So for this, we would use Rice Krispie treats, okay? So I have our Rice Krispie treats right here. I have 2 of them, right? So if you can, I'm sure you guys have used these as a snack before for your library program. So we'll go ahead and flatten these out. I would recommend flatten them out in the bag. It's a little bit easier. And also for this, you're going to need some red icing and some red sprinkles. And there are alternatives. You don't have to use these ingredients. I know some parents have qualms with, using a lot of red food coloring and things like that. And I can't say that these ingredients are the healthiest ingredients. Pretty high in sugar and fat. Okay. So we have our 2 Rice Krispie treats. And it says to make them, shape them into a rectangle about 2 inches by 4 inches. So let's see. Just flatten them out a little bit. You just use your hands with that. You can, your patrons, if you're dealing with younger kids, are probably going to want to eat them afterwards. And if you're okay with that, and if their parents are okay with that, that's fine. But they will have their nasty, I shouldn't say that, their possibly dirty hands all over these Rice Krispie treats. All right. So because we don't know a lot about the Mars interior, we're not going to do a differentiated core, mantle, or anything like that. We're going to place a glob of this red food coloring. I guess this is pink. Or excuse me, red icing. We're just going to place it right in the middle. So we'll take a big old glob of this, place it right there in the middle. Let me see if I can show you guys. So we're not going to spread it out. If you were to do the Earth model, you would spread it out and you would make it kind of a nice mantle around that, a donut hole core actually. So we have a nice little glob in here. We're going to cover it with this other Rice Krispie treat. Okay. This is probably, I'm not the best at this kind of thing, but your kids might be a little bit better with their tiny hands. All right, so we have a glob of icing in the middle of our Rice Krispie treat. I'll be honest, mine does not look that pretty. And then you're going to kind of fold it, shape it into a ball. What do you think? Would you?
I wouldn't let anybody near any books.
Yeah, I know. I'm not going to be able to close out the webinar because my hands are too sticky.
Right.
All right.
That's why I'm here.
Yeah, thanks. So we have our Rice Krispie treat planet right here. It has a molten, possibly solid, possibly liquid core in the middle of it. Right. So the next thing, of course, what color is the planet, Steve? What color is Mars?
Reddish.
Reddish. Okay. Rusty, I guess, if we could say. So this is a bag of red sprinkles, Jimmies, I've heard them called. Again, not very healthy, but definitely serves the poor. Wash hands before and after, absolutely, especially if you're going to let the kids eat this. So what I'm going to do, these bags are a little tiny, but any Ziploc bag would be good for this, or you could put it on a plate, and just let your planet, let's see, kind of get all of these red Jimmies all over it. right. Still plenty of white. We'll just say that that's the ice underneath the top layer. There we go. So I can't hold it up too close to the camera because I want to use my laptop, but you can see it's not perfectly uniform, all the jimmies over there, but it's okay. But it is covered in red. And then from there we could do some fun things like, could you hand me those chocolate chips? I feel bad for whoever's going to use this conference room after me. So we know there's volcanoes on Mars. Are there big volcanoes or are there little volcanoes, Steve?
Both.
There are both. So we have these little chocolate chips, just like you would put on a cookie. And we're going to put some tiny... This looks... Is this what your satellites pretty much observe? Right? We're going to put some tiny ones on here, these tiny little chocolate chips, and then to represent our big volcanoes like Olympus Mons. Are the close volcanoes close to the large? Are the small volcanoes close to the large volcanoes?
Not necessarily.
Not necessarily.
The small ones are everywhere. The big ones are only in a couple locations.
Okay. Make sure my dog's going to be excited when I get home. He's going to be licking my hands. Okay, so we have a very strange-looking Mars here. You might want to, when you put the chocolate chips on, put a little frosting on there so they stick to the top better. So at this point, you would want to get your cross-section. You could just have your patrons, have fun with their planets and eat it from here. But I would like to, the geologist inside of me wants to see the cross-section. So we're going to cut this Mars open. Easier said than done. All right. What do you think? You think that's what we're going to find on the inside of Mars?
Probably a little more regular than that, I expect.
So we have a stuffed Rice Krispie treat with strawberry frosting on the middle. When you do the Earth one as well, you use a donut hole to create a core, and then you kind of follow a similar process. There's a few more intricacies to it. So a fun, tasty treat. Of course, you can make it. You can alter it however you want, and you can adapt it however you want to. So, would you mind hitting the next button for me, Steve? It's that arrow right up there. Yeah. So here's a list of other Mars activities. I will send you guys actually, let me go ahead and put it on the screen right now, a list of all these links that you can download. It's a PDF, and I wonder why my computer didn't work, and it's maybe all these sprinkles on it. So that is a list of links if you would like to download them that just popped up. Actually, I'll put it over here near the attendee list. There's your introduction, Steve. And just a few last reminders. If you would, guys, if you wouldn't mind filling out the survey, just to let us know what you liked, what you didn't like. Probably didn't like the 10 minutes of technical difficulties. And then from there, you can get a certificate of attendance as well. If you need a certificate of attendance and you can't access it, yeah, that sounds good. I'd probably gain a little bit too much weight, Maggie, though, if we did that. If you can't access the certificate of attendance, send me an email, and I will send that over to you. So, again, thank you guys for bearing with us for those first 10 or 15 minutes.
Thanks.
Oh, that did work out great, Nicole, then. You didn't miss anything. It was all flawless. We hope you can join us again. May 17th will be Parker Solar Probe. In the meantime, feel free to shoot me an email with any questions or if you'd like any resources from this webinar. All right. Thanks, everybody. When I close out, you'll be redirected to that SurveyMonkey link. So we hope you'll take the time to finish that.
Thanks, everyone.
Bye, everybody.